First thing I'm going to do is to show you the kind of equipment that I'm using in my backyard today. This is exactly the same telescope and mount that I would have used if I were out at Silver City and we had hosts of people passing by and stopping to look through the telescope. This is one of the telescope types that Boyan told you about. It's one with an adjustable echelon. It's completely dedicated to the sun, which is a good thing and a strange thing at the same time. The only object this telescope can see is in fact the sun. And that's because it is only looking for the light of hydrogen. And on top of that, it is cutting back on the light that it's receiving, something in the order of to 100,000th to a millionth of the light available, which means that if I look at anything else in the sky, even the brightest possible object like the full moon, I can't see anything. So this is a dedicated telescope for the sun. Sits on a standard mount. No, I don't have a special filter on the front of this telescope, and that's because the filters are all inside the adjustable echelon that Boyan was telling us about. At the back end there on the left is a squarish looking object. That's the black and white camera that I'm going to be using. The reason for black and white is that since I'm not actually looking at colors other than the color of hydrogen light, and that tends to be red, there's no point in actually having a color camera. This also means that all of the pixels in the chip of this camera are dedicated to actually capturing that H-alpha, that hydrogen alpha light for me. That then feeds into my computer, and I will show you the software for that in just a minute here. So that's my setup, and this is what I'm looking at. What I'm looking at here, I know that Jim and Boyan are taking you through the difference between observing in white light and observing the sun in hydrogen alpha light, which is what this is. What we're looking at here, I've set up the software and the camera so that what I'm favoring is the detail on what people would call, in inverted commas, huge inverted commas, the surface of the sun. The sun, of course, has no surface. Forget the fact that it's too hot. You couldn't step on it. There's nothing solid to step on. It is indeed a ball of gas, which means that what we perceive as the surface is actually just the limit at where the light becomes visible to either our eyes or to our cameras. This is in fact what's called the chromosphere. The black and white images that Jim and Boyan told you about that actually show you things like sunspots, that's in a layer which is higher than this chromosphere, called the photosphere.
Oh, Simon, if I can interrupt. I'm sorry, can you switch screens?
Switch screens.
I'm getting messages.
Sorry. I'm glad somebody told me that. Hang on a second. What are you not seeing? We're seeing
your scope now.
Oh, goodness me. Hang on a minute. Oh, I see what I've done. I see what I haven't done. Good.
Thanks for those who alerted me to that.
Thank you. Very good. What have I done here? I'm going back into the meeting.
Near the top of the screen, Simon, you can change what. There you go.
I got it. We'll get there. Stop share, and there we go. Can you see that now?
Yep, that looks good.
All right. Now I just want to make sure that I can see what it is that you're looking at. Okay. There we go. Okay. So what I'm doing here is favoring the chromosphere, and in this chromosphere, you can see what looks like a moving picture of something very grainy, and it looks like something out of focus. Well, it's not. What you're looking at is the chromosphere of the sun through the Earth's atmosphere. And of course, we're looking through essentially a cylinder of heat coming directly from the sun, which means that the atmosphere, the Earth's atmosphere, is bubbling. It's churning. little bit like water on the boil in a saucepan. And as it does that, there are masses of the Earth's air which are warmer, and there are masses which are somewhat cooler. And so the light is actually refracting. And because our atmosphere is active, the image that we see of the sun is constantly in movement. But this is not the real movement of the sun itself. This is an artifact of the atmosphere. And this is one of the reasons why we try to look at the sun with the shortest possible exposures. Here I'm using exposures of about 2 milliseconds. That's 2,000ths of a second. If I go to 3 milliseconds, things begin to overexpose. Somebody asked Jim about gain. I'm about where Jim was, about a third of the gain capacity of the camera. You notice the sun is drifting slightly. I lined things up just simply using a compass this morning. And I'm almost aligned, but not quite. And so there'll be a little bit of drift, which will mean I'll have to pop out in a few minutes and pull the sun back into a position where we can actually see it. So what are you actually looking at with this hydrogen alpha light of this chromosphere? What are these granules? Well, some of them, you can see there are some small dark spots. And one might think that's perhaps dirt on the camera. It's not. Those are small areas of convection on the sun. The sun is hotter inside than it is outside, which means that the hydrogen gas in the outer parts of the sun rise, rather like bubbles of hot porridge on a stove. They rise, they reach the surface, and they start to cool. They spread out laterally, and then the cool material sinks back into the sun. Now, these small granules, let me perhaps show you one here. Annotate. It's very small. Let's pick this one right there. There we go. The left end of my little stick here, that's pointing at one of these things I'm calling a granule. That's probably somewhere in the order of, hang on a sec, I'm trying to clear my line there. Doesn't want to clear. Let me do it that way. Let me do it that way. There we go. That little granule is probably of the order of up to 10,000 kilometers across. Order of magnitude, it's not far off the size of the Earth. And these are all over the sun, but you can see that there's more to it than that. There's a network, which is sometimes difficult to focus in on because of the way that the sun is apparently moving in the due to atmospherics. But here's one that I want to show you. There's something here, like a big circular cell. That's referred to as a megagranule. That is something of the order of between 30 and 50,000 kilometers across, which means you can stick quite a number of Earths in there. But it's a very, very similar phenomenon to what we were looking at with the granules themselves. Let me clear my line off of there. So the sun itself is literally in a boiling state. And as it's boiling like this, you have this movement of this very, very hot hydrogen in a gaseous state. And because it's so hot, it's ionized. And because it's ionized, that means it has an electrical charge. And as electrical charges move, they generate magnetic fields. And you all know about magnetic fields. You know the Earth has a magnetic field. Luckily for us, it has a fairly simple magnetic field. Our magnetic field on Earth has a north pole in the north and a south pole in the south. It's not always that way, by the way. The magnetic field does switch, but let's not worry about that. But the sun is way more complicated. The sun has magnetic fields with north poles and south poles all over what we would refer to as its surface. And you can see them quite nicely in the chromosphere here. And this means that when we talk about the activity of the sun, we're actually talking about its magnetic activity. And as I said, this magnetic activity is very complicated because the convection pattern of the sun is so complex. At that point, I'm just going to take a quick break there, and I'm going to move that sun back into position. Don't go away.
I've got a couple of questions that I'll ask Simon once he returns that have to do with sunspots. And we've had a couple of people who have asked about the overview of the day, the full schedule. So I've mentioned that it's on the RASC Ottawa website and also on the YouTube feed. So I'm hoping people can find that if they're curious. But of course, we will be displaying the full schedule during all of the breaks.
Okay, I just bumped my scope. It's going to take me a minute or two to get it back in line.
Okay.
While he's out, hey Doug.
Yeah.
While he's realigning, I could answer some of those questions if you like.
Okay, that's great. So Keelan's asking, can you explain sunspots on the sun? And Amar was asking, why do the sunspots, if I'm interpreting the question correctly, why do sunspots have a minimum at the present time?
So I'll answer the last question first. So we don't really understand why the sun goes through the cycles. It's something that's been observed for hundreds of years. People have been recording the size and the frequency of sunspots for a long time. And the fact that there's a cycle of activity has been known for quite a long time. Why it happens, we do not know. It's something to do with the how the sun works physically, how it generates magnetism, but we don't fully understand why it happens. We just know that it does. We also have observed that the magnitude of each cycle, so how low the minimums are and how high the maximums are, does vary with time. And there seems to be some correlation with climate on the Earth, but the link is still being researched. So the first question about the temperatures or what is a sunspot, it is entirely to do with the temperature of the gas that we're looking at. We're still talking temperatures in the 5,000 to 6,000 degree Kelvin range, but material that is cooler appears darker. And so it just happens that where there is a focus of magnetic field lines coming through the photosphere, it has an impact on the temperature of the hydrogen gas locally. And we see that impact as a dark region. Hope that answers the question.
I think so. Waiting for anybody who was asking those questions for any follow-up questions. We're waiting for Simon.
The full schedule, by the way, is available on the Astro Day Ottawa website.
Okay.
That's astrodayottawa.weebly, weebly.com. So the whole day schedule is on there.
Thanks, Jim.
You're welcome.
Oh, sorry about that.
Okay.
Now, let's see if I've got control of my computer here.
So, Simon, I have another question who's coming from Galaxy S10. I don't know. I guess it's an anonymous smartphone device. So are the last elements in the periodic table only found on our sun, like Newtonian and Einsteinium? Do you have any thoughts on that?
Oh, if they are, they'll be deep, deep, deep down inside. They'll be actually in the nuclear reactor of the sun. What we're actually observing here is the outer layers of the sun. The nuclear reactions are taking place way in the core of the sun.
Okay.
Okay. Got the sun back. I just have to make an adjustment to focus.
And just a note about the schedule to follow up with what Jim was saying. We're having at 11:30, we have Jim back with some more live sun observing. We have a break for an hour at starting at 12 and of course ending at 1. We go back to Simon for some more sun observing at 1. At 1:30, we have Bejangon who will do some more live sun observing, and then Jim takes over for some sun observing at 2. At 2:30, we have Jean-Sebastian will have an introduction to telescopes and mounts, and at 3 o'clock, Attila will take a closer look at telescopes. 3:45, Jim returns with some more live sun observing. Okay, thanks, Simon. Take it away.
All right, so we're back looking at this. I just want to make a slight adjustment here, see if I can get things a little sharper than they are. You might be wondering why I'm having to actually leave the computer to go out and make adjustments to the telescope. It just so happens that my backyard neighbors are having a wedding today. And they decided to start their wedding at 11 o'clock, just when I was supposed to be starting talking to you about the sun. So I have had to move everything as close as I can to the house and get myself inside the house, close the door so they can't hear me talking in the backyard while they're exchanging their vows.
Are they social distancing, eh?
Well, we won't talk about that, will we? Now, I just want to be sure that you're seeing more or less what I'm seeing. Okay, so we're looking at this bubbling in the sun. Normally, I mentioned that this bubbling is what's responsible for the complex magnetic patterns that one sees on the sun. So what exactly are these famous sunspots that we're not seeing right now? Boyan has told us about and showed us pictures of, and I believe so did Jim. These, of course, are expressions of these complex magnetic fields in the sun. And they commonly occur in pairs. We don't have any today because the sun is being very, very quiet. And I'll come back to this in just a second. And the sunspots are often in pairs. And the leading pair will be the leading sunspot in the pair, leading in the sense of the one that's actually in front with respect to the rotation of the sun. It will be of one a magnetic sign, so it might be positive, negative, north pole, south pole, and the other will be the complement. And it turns out that the sun actually goes through an 11-year cycle where you get more or less sunspots. We're right now in a low of that 11-year cycle, and therefore not seeing much in the way of sunspots. And in any event, it turns out that this particular cycle that we're going to go into is a very quiet cycle. There's not much in the way of activity, magnetic activity predicted. But it turns out that the remarkable thing is that when the cycle switches from one cycle to the next, the sense in which the sunspot pairs are magnetized, that switches as well. And this is how it is that astronomers who are looking at the end of one cycle and the beginning of the next cycle can tell whether a sunspot pair belongs to the old cycle or the new cycle. They simply look at the sense of magnetization and they say, oh, well, the old cycle should actually have the leading sunspot being, let's say, North Pole. And here we have a sunspot pair where the leading sunspot is South Pole. It must be part of the new cycle. But this lack of sunspots right now has raised some fundamental questions about solar science. And I was just reading yesterday that there's a group of university scientists who are asking themselves, what happens if we try and compare our sun, as you're looking at it today, with similar stars elsewhere in our galaxy, which are the same as our sun. Our sun is what's called a yellow G dwarf. we might not think it's very small, but compared with other stars, it's actually not that big, which is one of the reasons it's so stable and one of the reasons it's lasted so long. And as they look at other stars, they've compared this, our sun, which is a star, with about 350 other stars of a very similar type. And they find that our sun is extremely quiet. In other words, they're saying it's not just quiet because we're in the low part of the cycle, the 11-year cycle, and it's not just quiet because this is a particularly quiet 11-year cycle that's coming up. They're suggesting that our sun might be actually being very quiet on a scale of maybe 10,000 years. And therefore, what that would mean is that although we, both amateur astronomers and professional astronomers, we like to look at the sun and tell people, this is the only star on which you can actually see what a typical star looks like. It may be that what we're looking at on our sun is not what our sun typically looks like at the scale of its lifetime. And remember, the sun has existed for about 4.5 billion years. So if the sun is in a 10,000 year quiet period right now, that's literally nothing more than a snap of the fingers in terms of the lifetime of the sun itself. So it's an interesting notion. It's a hypothesis. This is not yet is established as a mainstream school of thought. But is the sun, as we're looking at it today, typical of the sun as we would see it elsewhere? Now, I'm not going to mess around by trying to go out to that that prominence that Jim was showing us before. I'm going to leave the scope here focused on the granularity of the chromosphere. I'll go to that prominence in the second session if the sun is still available at about 1 o'clock-ish. But right now, the important thing is you can probably see that already over the last, I would say, 20 minutes, the atmosphere, the Earth's atmosphere, is already degrading our image. The image is coming in and out of focus. That's atmosphere. If I were to go up and start playing around with the focus on the scope, I could probably improve on this right now, given that I have to step outside and I've only got about another 5 minutes to go. I'll not do that. But this moving in and out of focus is fairly typical as you move through the day. The best time for observing the granularity of the sun is early morning after sunrise, because the atmosphere itself hasn't started to heat up. And a colder atmosphere is a more stable atmosphere. From around about midday into early afternoon, it becomes difficult to actually chase the focus, because you get in focus and then within a few minutes, the atmosphere has changed and you seem to have come out of focus again. So one of the ways of observing and capturing the sun, as opposed to trying to capture an image of your holiday snaps or an image of a galaxy or a planet, instead of taking a picture with as long an exposure as you can get to capture as much light, with the sun, because of this atmospheric effect on focus, what I do is I set up my camera and start capturing images maybe every 10 seconds, but images with an exposure of 2/1000ths or 1/1000th of a second, and then maybe capture several thousand of these, then ask a piece of software to tell me which of the images are best in focus and which are most out of focus. And as you can see, over a period of seconds, it's changing.
Simon, I have a question.
Yes, go ahead.
Are what we're seeing, is part of what we're seeing the sun spinning? And if so, what keeps the sun spinning? I have a question from Chobe on that.
The sun spins because of the way that the solar system formed. The solar system formed from a cloud of gas which collapsed. And as it was collapsing, it was turning. The cloud of gas itself already had a certain amount of movement to it. As it collapses into a disk, so it builds up what one would call angular momentum. And this is why the planets all go around the sun the same way, and why the sun spins in the same direction as the planets are going around it. And the axes of spin of all of the planets and the sun, with one exception, and that's the planet Uranus. They all spin with their spin axes more or less at 90 degrees to the plane of the solar system. So the reason the sun spins on its axis is because of the way the solar system formed in the first place. The sun is spinning, but it's not spinning like, say, the Earth is spinning on its axis. We are a solid ball of rock. And so everything turns such that the night-day cycle is 24 hours wherever you are, whether you're on the equator or whether you're on one of the two poles. But the sun is a ball of gas. And so the equator is actually rotating at a different speed from the gas at the poles. On average, the sun takes about 25 days to do a full rotation. But nearer the poles, I believe it's a slightly longer period. So that's the sun spinning. It's spinning, it's turning. Jim mentioned this, so did Boyan. But it's not turning fast enough that you would sit there and actually watch it, unless you were watching for the whole day and washing something out right at the margin. And one of the prominences that Jim showed us, for example, could either come over the horizon as the sun is spinning, is turning, or go over the horizon and disappear, depending on which side you were looking at. And so that leaves me with what, about 3 or 4 minutes.
Yeah, got another question here, Simon, if you can hear me. Yep. Keelan's asking, will the sun ever lose that momentum before it completely burns out?
No, it's going to. Although it's going to take another 4.5 billion years for the sun to actually shut down. I'll very briefly explain what that means. It will continue to turn. It's been spinning, but things have been rotating stably for the last 4.5 billion years, and that is likely to continue. The change in spin of the Earth, for example, we know that days were shorter back in geological time and have grown progressively longer. That's related to our gravitational interaction with our moon. And our moon is moving away from the Earth. There's an exchange of gravitational energies and an exchange of angular momentum, which is why the sun is slowing down as the moon moves away. But the planets aren't doing that with respect to the sun, certainly not today. They may have done in the past, according to one major hypothesis. But right now, the planets are pretty much stable in where they sit with respect to their orbits around the sun. So there's no gravitational interaction trying to slow the sun down. But the sun will not last forever. It will eventually turn into what's called a planetary nebula, which I'll tell you something about. Will I be telling you about planetary nebulae? Maybe not. Which is basically a situation where the sun, as it starts to use up its nuclear fuel internally, begins to actually cast off its outer layers. And they get cast off as a sphere of gas. And when we look at stars that have done this in the astronomical past, we can sometimes see stars surrounded by what look like bright rings. There's one called the Ring Nebula, for example, which is the classic of the genre. And that's where our Earth is headed. It will then leave probably a white dwarf star behind, which is something much, much smaller, but much, much denser than the sun we have today. But that's for 4.5 billion years down the road, so don't panic and don't sell the farm yet.
Well, thanks, Simon. That's all the time we have